I can't find the computer monitor, so we're not going to do any computer stuff today. I think some fraction of you are, whether you understand it or not, you're sick of the computer stuff, so probably it makes you just as happy. Nonetheless, even if sick of it or not, I can't explain it to you. Now, take out your clickers. I can still vote here. Okay, first vote is, do you have MATLAB on your computer? Or no, we did this vote before. I just want to see it again. Yes, you do. No, you don't. Do you have MATLAB on your computer? Yes, you do. No, you don't. Okay, so it's almost exactly 50-50. Those of you who don't, means you can't work on the homework over Thanksgiving. So that means that there's only, if you like, 4 days to do the homework. Today, yesterday, today, next Monday, Wednesday, whatever. So if you want an extension, you get it. You can hand it in Thursday afterwards, the day of the final class. But I recommend to you that you get MATLAB on your computer, because most of you are going to take CS with MATLAB. Those of you who don't are going to take an extra MATLAB class. You will use it in your later classes. And this idea that you're supposed to become a MATLAB hacker, I know for some of you I've totally failed. And all you do is drag yourself through your homework with your friends helping you and so on. But for those of you who I could win over, and I still like to win over a few more of you, you should be thinking, oh, this is MATLAB, I can use it for other classes. Okay, vote number 2. Are you ready? Vote number 2 is, I have used MATLAB at least one time for one thing, at least one thing which was not assigned in any class. Yes or no? Okay, we're up to 32%. Very good. Okay, next. There was a question about when the final project is due. This is the final project report for your car. We always intended for it to be due on the Monday after the Saturday after Thanksgiving. That's the Monday, which is the first day of study week. Somehow I think it got misposted and people thought it was due after that. That was due to a communication error between Anoop and myself. Does anybody, okay, do you have a problem with that? Let's just find out. Vote. A, that's fine with me. B, I was counting on it being due later than that. We had always intended that it be due the 7th. Somehow it got misposted as the 14th, which is illegal. Not only wasn't it our intent, it's not allowed. How many people are upset in some way or disappointed about that, it being the 7th instead of the 14th? I am disappointed. A, I'm not. B. What? A, I want...
You changed the question.
Oh, sorry. There's no resolution to that. I am disappointed. A, I'm not disappointed. B. A, I was hoping for it to be later. Okay. What we can do, but it's just bad for you, it's like letting you get yourself in trouble, is on person by person basis, we can let you hand it in late. In other words, we can't make it due late, but we can give you an extension. It's like a way of breaking the rules. Now, the thing is it's a bad thing to do, because the reason there's no final exam in this class, the reason we don't have stuff due later, is so that those final few days of final exams is like one thing you don't have to worry about. It was intended to be nice. Now, by being nice and letting you hand in the project late, I am being not nice. So we're going to make you, if you want to hand in late, you have to ask for it. And with each permission, we're going to say, we do not recommend this. Because it's like getting yourself in trouble, right? Is that clear? Yes? Any problems with that? Any comments or questions? Okay, next. Past several weeks, we've been doing two things which are going over the heads of some of you, and some of you are thinking is confusing. Two things are things having to do with gears, A. B, things having to do with functions in MATLAB, and one function calls another function, and you have an @ symbol, and there's a global variable, and it's hard to pass variables and all that stuff. I'm not today going to talk about all that confusing computer stuff. I do think you should try to untangle it, not just copy things from your friends. You have, obviously, some of the syntax, every now and then you have to copy a little syntax, but you would like it sort of in your control, that you know how to figure it out. Gears, however, I could talk about. Who would like me to talk about gears a little more right now today? Raise your hand. Okay, that's most of you. So I'm going to talk about gears for a little while, and then I'm going to go on and talk about friction. First off, something about pedagogy. Some of you think I'm making things especially unclear. Can't you just tell us how to do these calculations? And I would like to just say, I can make it clear. If I think of a kind of homework problem, I can tell you a recipe for doing that problem. I am not trying to teach you recipes. I'm going to say the same thing again 3 more ways. They have an expression for human aid in Africa, say, and they say you can teach a man to fish, or you can give a man a fish, or you can teach him to fish. And the whole idea is good human aid is you teach people to fish, or you can give somebody food, or you can teach them how to farm, or you can give them food, or you can give them a shovel. And the idea is that it's considered better in the long run for people if you give them the tools for doing things rather than just give them the thing. Now, in teaching, it's like that with recipes. If you give a very clear recipe for doing a problem, or really spec out a very clear algorithm for doing something, in a way, you've given people nothing. Now, on the receiving end, it's incredibly frustrating if, say, you're hungry and somebody teaches you how to farm, and therefore you have to starve for 6 months before you get any food. That's what it's like. You want to get through the homework and someone doesn't give you the recipe you need. It doesn't feel good. But you're young enough so you can afford that pain. And I am intentionally imposing that on you. It could be that you say, I'm rationalizing the fact that I'm a confusing teacher, but I don't think it's entirely the truth. I actually can't stand just teaching people recipes. Now, lesson 2. You are human beings, you are not computers. Those things that we can teach you in very clear recipes are exactly those things which we can program into computers, and therefore are not worth teaching. So we do not, for example, teach anymore how to calculate logs to 6 digits, even though they're very clear recipes for it. We do not teach how to calculate square roots to 5 digits. We do not make you go through the long division algorithm and calculate 7 digits of long division. They don't emphasize that in school anymore so much. Why? Because there are calculators that do that for you. Similarly, for solution of ordinary differential equations, of course you have a class in it that's coming up where you have to learn something about pencil and paper methods, but there are all kinds of advanced methods for solving ordinary differential equations which we do not emphasize because we know how to program in the computer. So there are things, for example, how to deal with gears, exactly how to deal with some motor, some gears, some car problem. I could write a recipe for you like this, plug in this formula like that. It would have no value to you. Because the probability if you're running into exactly that problem is small. And if it was common, it would be a button on the calculator. Same with the MATLAB stuff. I could show you exactly the syntax for this and that, And I have to show you some of that at the beginning. That's why you go through the tutorials. But if I show you exactly how to do this and that, that will show you how to memorize that particular thing. It's not what you need. I'm going to say it now one more way. Just to show, this is to show you my sympathy for your situation. The word processing that I do is a program called LaTeX. And I use it in a very complicated way for a book that I'm writing. If anybody wants a copy of the book, you come to me, I give you a copy of the book. Statics and Dynamics. Free. If you come to my lab and ask for it. The LaTeX in that is really complicated. I get stuck all the time, and when I get stuck, I look for help. Some of the sources of help try to teach me the philosophy of the language and how it works. And I want to wring the necks of the people who do that, because I just want to know how to indent something or put a box someplace or put a figure on some page. I don't want to know the philosophy of the language. I know what that feels like. And I know when you're doing your homework, and I've just showed you a bunch of stuff about the ideas, and I don't tell you which formula to plug in where, that's what it feels like. So I feel your pain. I know what it's like. The price I paid for it is I still don't know how to use this language, because I'm just trying to get through one thing at a time. And probably had I yielded to those in the help manuals that are trying to teach me the whole philosophy of the programming language besides this, behind this typesetting program, I would have been better off. Whether or not that's true, I'm trying to do the same thing to you. Everything clear? Now still, I know some of you are thinking, I just want to know how to do the homework. He's completely confusing. Just tell me how to do it. But nonetheless, I'm just telling you, this class is not a prerequisite. This particular class is not a prerequisite for anything. There's no skill I'm teaching you here which somebody's going to demand that you know. I'm thinking some of the things are useful, but I'm trying to get you to get in the habit of problem solving, and that includes figuring out how to untangle the MATLAB and figuring out how to untangle this gear stuff, for example. And same with the hydrostatic stuff, and same with the structural stuff. Okay, so now let me just talk a little about gears. Any questions about that philosophy or comments or criticisms? How many people thought it was clear what I just said? Not clear? Okay, now private vote. A, you're sympathetic to what I said. B, you basically resent what I just said. Okay, so those of you who basically resent it, I know some of you do, and I'm not going to keep track of who it is who says they resent it. But maybe we come talk to me. I'll take you out to lunch. Does the vote go way down or way up when I make that offer? Okay. Gears. There's a presentation in PowerPoint that Professor Zender, the chair of Theoretical and Applied Mechanics, the department formerly known as TAM, wrote. And it says, what is mechanical engineering? So it's a 1-hour version of this lecture. Some of you have seen it. Slide number 1 says, mechanical engineering is about the manipulation of energy, moving energy, something like that. There's some fancy words for it. Manipulation of energy. If you read that slide, it makes it look like all of mechanical engineering is about gearboxes. Energy in, energy out. So gearboxes are about energy in, energy out. So they're ways of transforming energy. Now gearboxes are different from some other kinds of energy out, like an engine which takes chemical energy in and mechanical energy out, or electric motor, electric energy in, mechanical energy out. It takes mechanical energy in and mechanical energy out. And what comes in can be into the gearbox typically is something from a motor. And from a motor we have two things that are coming in as this torque and an angular velocity. Now most gearboxes, you think of this torque in, this angular velocity in, you think of some torque out and some angular velocity out. But actually, in the end, if we take the whole transmission, often the final job we want isn't one of rotation, it's one of translation. So for example, with a car, even though you have all these rotary parts, and even though the last thing in the line is a wheel, the job of the wheel isn't to rotate, the job of the wheel is to push the car forward. So ultimately what we care about is a translation, and that's associated with a force out and, say, some velocity out. So it's still a gearbox, it's just that the inputs and outputs aren't in the same units. And so we think of the car, transmission, your gearbox in your car, your belt drive, your underneath old cars, they used to have a axle down the middle. You can see it underneath trucks. What's it called? That power thing under a truck with universal... What?
Drive shaft.
Drive shafts. And it's got a universal joint at each end, and then there's a really fancy thing in the middle of the back of the car. There's a differential, and it goes to an axle and the wheels. The whole thing, though, takes torque from the motor and puts it into a forward force and a forward velocity of the car, or if you like, a forward velocity, backwards velocity to the bottom of the tire of the car. Now, when we talk about gearboxes, this is the thing we're talking about. Now, the usual model of the gearbox, which is not completely accurate, is that the energy in, or the power in, equals the power out. So we say the gearbox is a passive device, and not only that, it's got no friction. And one of the uses of the word friction, which I hope to get to today. The word friction has lots of uses, but you say there's no dissipation, no loss of energy. Energy in equals energy out. So what this means is that the torque in multiplied by the angular velocity in, that's the power coming into this, is equal to the torque out multiplied by the angular velocity out. Or if it's another kind of gearbox, it's the force out multiplied by the velocity out. Okay. Any questions about this? Where is there some subtlety, which is sort of mechanics that you should think about, is why is it that power is both force times velocity and torque times angular velocity? I explained it quickly in one lecture. It's something for you to think about. It's something I can explain again now. But if you like, when in doubt, lots and lots of mechanics things can be figured out by thinking about teeter-totters. And we can think of some force times some velocity of some point here, which is the power going into this end of a teeter-totter. But this force is equal to the moment it's causing divided by the radius, and this velocity is equal to the angular velocity times the radius. And moment, let me just use the word torque here instead of moment. So the product of torque and angular velocity is the same as the product of force and velocity. So whenever you talk about torque, you're actually talking about some distribution of forces. Whenever you talk about angular velocity, associated with that is the velocities of a bunch of points. And if you take all the different forces and look at the torques they cause, multiplied by the velocities of those points, it adds up to the same torque times angular velocity adds up to the same thing as force times velocity. Okay, so this is making the assumption of a so-called lossless transmission. Are real transmissions lossless? The answer is no. How about the gearboxes in your cars that you're building, the ones that we passed out that cost $8? Are those lossless? No. How much do they lose? Any guesses on that? Anybody attempt to measure it? You did? Did you get a number? It loses 25%. So it's that sounds about right. So about 75% efficient. I'll just tell you a rule of thumb that you can remember is that if you can backdrive a motor, in the case of your car, it means if you can take the wheel and turn it and have the motor spin, then it's usually more than 50% efficient. If you can't backdrive it, it jams, it tends to be less than 50% efficient. So rule of thumb is if you can't run it backwards, it's probably less than 50% efficient. 75 sounds reasonable for those plastic gears. Okay. Now, what does this mean? Well, over here, driving this thing is some kind of motor. It could be a muscle of a person on a bicycle. It could be a motor, a gasoline engine. It could be an electric motor for your car. And over here is the thing that you care about, your output. In this case of your car, it's like this. Here's your output, the force of the wheel on the ground. Now, when the motor runs at different speeds, it can supply different torques. That means when you get different forces, when the bottom of the wheel is running at different speeds, you get different forces. But how these are related to depends on the gear ratio. So the gear ratio affects these numbers. And we keep talking about the gear ratio. It has to do with amplification or attenuation. Here, it's a straight dimensionless number. Here, it's not a dimensionless number. It has to have dimensions of length or reciprocal length. But still, it has to do with the relationship between the input and the output. So how did we work this out? We said that we're using the gear as a gear reduction. So when you have a fast motor and a slow output speed, we're calling that a big gear ratio. So that means this is this omega in divided by the gear ratio. And in order for energy to be conserved, this has to be G times the moment in. And this is this idea, again, which I tried to show you over here with the teeter-totter. Really is true that the teeter-totter can give you an explanation of things. You want to figure out a gear ratio here. It's, say, a relationship between the force you get here, the force you get here, or the torque you get here, the different ways to think about it. But anyway you think about it, the further you move this point out and apply it, the bigger the so-called gear reduction, which means the smaller the motion here for a bigger motion here, yet the bigger the force. So there's this duality. So if there's one thing that I want you to learn in this class, is you can't think of a gear as something which just multiplies, because if it multiplies motion, it divides force. Or if it multiplies force, it divides motion. You can't get both, because energy's got to be conserved at best. Yes?
How does MI relate to Q?
How does what?
MI. Force out.
I use the word torque. I use as a synonym for a moment. So sometimes I use the letter M here, and sometimes I use the letter T. And there's so much synonyms in my mind that I forget which letter I'm using. Okay, so what comes out of this is this funny graph, and this is this graph that I've been trying to get you used to, which is that for electric motors, a given electric motor, we can characterize by any two of four numbers: a stall torque, the how fast it runs when it's free, the peak power that the motor is capable of achieving, and the slope of this line. But when we put it through a gearbox, we get out of the transmission. In this case, we're looking at a force out and the velocity out. We get a straight line again, and here we get our velocity free, our stall torque, we get our peak power, but the peak power that we can get out is the same if we assume that it's a lossless transmission. If it's not a lossless transmission, this curve is going to shift, and we have a slope here, C prime, which is not equal to C. Each of these numbers is related to the other numbers. So the peak force is equal to the peak force. That connects these two things. The peak power is the peak power. This F out, that was the thing which we said is the gear times the moment out. The velocity free, that's the thing we said is the omega free divided by the gear ratio. And then the C and the C prime, we have the C prime. Well, C prime is, on the one hand, we have the C is equal to this M0 over omega free. This C prime is equal to F0 over V free. So this C prime is the ratio of this to this, and that would be on the one hand is F0 over V free. On the other hand, we can make the substitution, and it's M0 over omega free times G squared. Okay, now I wrote this all on the board 2 times now in 2 different lectures, but what this means is the same way you did experiments in the lab on the motor properties, where you tried to take the gear ratio into account. On your car, once you've already built the car, you can try to just do direct experiments on the car and figure out these things. For example, on the whole car, the V free would be the total speed of your car when it's going at full speed. And that's taking into account all the transmission losses in the car. And your F0 would be your stall torque. That's the biggest force the motor can apply. So you can directly probe your car for this curve, even if you want forgetting this curve over here. Then what you know about your car is that if you change this gear ratio, you change this curve. You change it in such a way that the peak power stays about the same, but you can make the stall torque bigger or smaller depending on changing the gear ratio. For example, if you took a car and found out the biggest force it could pull, assuming the wheels are not skidding, is this. If you put smaller wheels on the car, that's effectively changing the gear ratio. And it would take this curve and move it up. You would have a bigger force it could pull with smaller wheels. On the other hand, with smaller wheels, it would be a slower peak speed that it would go when the wheels are spinning freely. With the same, it would be a different curve, but the peak power would stay the same, assuming the friction didn't change when you made that change. Okay, who's following everything I said? Raise your hand. Okay, somebody ask a question, or make a clarification or something. Yes?
Why would the stall torque increase when you decrease the size of the wheels?
Why? It's not the stall torque of the motor that increases. Okay, so what you have on the car is this wheel, which is being pushed by some force here. If we draw just a free body diagram of the wheel itself, there's some forces at the axles which don't matter. There's a torque coming to the wheel from the other part of the gear train. Let's just say this is some fixed. This is the torque on the wheel from the motor. And then we have some force over here, which is the one that we're interested in, this output force. If we keep this fixed, I'll just call this torque on the wheel to make it simple. We keep this fixed, assume that the friction in the axle is negligible, then this force times this radius has to balance this torque. If we put a smaller wheel on, this torque stays the same, so the product of the force times the radius has to stay the same, so the force has to go up. Okay, so what does that mean for your cars? Is if you want to win the pulling competition, you want to put teeny wheels on. How teeny? The teenier the better. Except for one thing, which is friction. And how come? What do you mean except for friction? Friction helps you. What's the problem?
Your wheels might skid.
They might skid. So if you make the wheels smaller and smaller and this force gets bigger and bigger, you start to exceed the frictional strength of this contact. So now I want to switch topics to friction, unless there's more questions about the gears. Gears clear? Just one more thing about the gears. The subtle part, the part that I'm making you suffer through with this MATLAB code and so on, is that when you pick different gears, you're picking different curves here, and each one is good for a different job. For example, a very low gear is very good for pulling huge forces here. It's very good for having a big power at low speeds, but a very low gear stinks because it only goes so fast. On the other hand, a very high gear, which corresponds to a low gear ratio, is flat like this. The car can go very fast, but it can't apply a very big force. So it has trouble accelerating. And not only that, if there's any resistance, it might not be strong enough to fight that resistance. For example, on your bicycle, when you're in a high gear, one that you can go really fast in, if you get to a slight wind, you can't go at all. And if you're in a very high gear in a car and you get to a slight hill, it doesn't go up the hill. That's a low, what I call a low gear reduction. High gear is a low gear reduction. So you want to pick your gear for the job, and that's what I've been trying to show you by means of all these complicated calculations, how to actually calculate the effect of a different gear in a different circumstance, and how to optimize it. Clear? Okay. Now, friction. When I was in high school, and again when I started college, I hated friction. I hated it because simple calculation tricks that work in high school physics, elementary college physics, don't work when there's friction. Like conservation of energy. Your intuitions about how things work don't work when there's friction. The basic equations of friction are not very accurate. They're not like Newton's laws, force balance, momentum balance. So friction is dirty. I didn't like it. I just didn't like it. If you would have asked me what do I think about it just as a subject, I just didn't like it. There's a theory of knowledge, which is that whenever you learn anything, like as I'm teaching you things, when you learn them, a little switch goes off in your head, each of you, and you categorize every little bit as a good fact or a bad fact. Like 2 + 2 is 4, you categorize as good or bad. Everything you know, somehow one little part deep inside you categorize as good or bad. I used to think friction was bad. But God was listening and made me do a PhD thesis in friction. So I turned from hating friction and avoiding it to completely indulging in it, and now I love friction. Friction just switched from bad to good. Okay, so what's friction about? So I wrote a PhD thesis for the past 25 years or so since I published it. Every 2 weeks, somebody else writes a paper using my thesis to do something else. 500 people have done that so far. Okay. What's it about? The simplest kind of friction, or the one that mostly people are talking about when they use the word friction, is this idea of solid contact. Now this is only one of several uses of the word friction, all of which are subtly connected to each other. So you talk about air friction, people talk about rolling friction, they talk about transmission friction. Even in electrical circuits, sometimes people talk about friction. So the word friction is not one precise thing. It's slightly different things in different contexts, sometimes very different things. But the main use of the word is about solid contact. And what it's about is when you have two things touching each other like this, that there's some force of interaction between these two things. So what you do is you separate these two things in your mind as if you were drawing a free body diagram. But I'm not going to draw the whole free body diagram. I'm just going to draw that part which shows the interaction between these two surfaces. And what you see is that there's a force on one of them and a force on the other one which is equal and opposite. That's the law of action and reaction. And there's a normal force and a normal force. So we cut these things apart and we fool them into thinking they're not cut apart, and that's the interaction between them is these two things. Now meanwhile, this point, let me call this thing B and let me call this thing A. This thing is going to the right relative to that one, and I'll call it VA relative to B. So this is the velocity of A relative to B. Now why do I put velocity of A relative to B? Because sometimes when you have friction, neither of the two things is still. When you're dealing with your wheel in the ground, one is still. Often one is still, but not always is one of the things you're interested in still. So there are various laws of friction, and there's Jaeger's 3 laws of friction. So one of the, law one, is that friction doesn't depend on area much. Now, how do you know it does depend on area a little bit? It's because in big fancy racing cars, they put this really soft rubber, so there's lots of area of contact on the ground, so they get more friction. On the other hand, how do you know it doesn't depend on area very much? Is if you take, say, a block of wood, and see what slope it takes for it to slide, that slope will be pretty much independent of whether you put it on the small surface or the flat surface. Not exactly, but pretty much. Then, Jaeger's second law is that the friction coefficient is something in the range of about 0.1 to 1, usually. And what's this about is that the friction force in sliding, so when something is sliding, the magnitude of the friction force is equal to mu times the normal force, and this mu is called the friction coefficient. And sometimes people define a friction angle, which is the slope of the combined force of the friction force and the normal force. And so there's this friction angle phi. And you can specify the friction angle of a material pair or the friction force. And then Jaeger's third law, which is what I learned best in my PhD thesis, is this one. Now, Noop is getting his PhD in mechanics. He studied friction in lots of courses, and I bet he doesn't know Jaeger's third law of friction. Do you know it? Jaeger's third law of friction? It's the most important. Is Jaeger's third law of friction. A friction experiment will make a monkey out of you. Now, why is that? There are hints of it in the first two laws, which is that it's just not, friction is, you can count on there being some of it there, but you can also count on not being able to characterize it accurately. If you really, really carefully try to figure out what's going on with friction, you'll never figure it out. And that's like, I did a PhD on not figuring it out. First of all, the effects, there are all kinds of weird, subtle effects. And second of all, they change from day to day. They change depending on the humidity, the sunshine, who knows what. Can't control a friction experiment as far as I can tell. Okay. So what's the basic idea, though, is that you don't have to worry about the area of contact. You do have to worry about the normal force. The harder things are squeezed together, the harder it is to slide them. And so you can make a graph, and this is a very good graph. It's not in enough books, so this is one that you should just look at. You can refer back to your notes when friction comes up again. And what you make a graph of is the velocity of A relative to B. And on this axis, we put the ratio of F to N. And this is our characterization, our constitutive law. Remember, all of mechanics is built of three pieces: the laws of mechanics, the geometry, and the constitutive laws, the material property. Here's the characterization of the material property for sliding. This is the analog for sliding for what we had in elasticity. If things are elastic, we have Hooke's law. For fluids, if they're deforming, we have this viscous law of deformation. And now here's the here's the most classic law for how things slide against each other, is this curve. So the curve is shaped like this. And this is the classic description of friction. That when the two things are sliding on each other or not, they are stuck on this curve. And this curve takes into account whether it's sliding or not sliding. So a common mistake when people start working with friction is they take this equation F equals mu n, which is in some sense the basic equation, and that's applying to this part of the curve. F is equal to mu n. In this part of the curve, we have F is equal to minus mu n, which you could say is the same equation if we had our signs right. And in this part of the curve, we have that the magnitude of F is less than or equal to mu n, and that's the no sliding part of the curve. So you have three different equations or inequalities depending on whether the two things are sliding to the left, sliding to the right relative to each other, or not sliding at all. Yes?
What is mu? Mu, I mean, it's just like, it's
Mu.
the end though. I mean, on the graph.
What?
I don't see what it's connected to. You've got,
It's connected to this point here. It's connected to this point here. Does that help you?
yes.
Okay.
Oh, yeah.
Mu is a material property. What's the value of it? Usually it's between 0.1 and 1. What's an example of materials where the coefficient of friction is about 1? Say rubber bands on rubber mats in the second floor of Upson. What's an example of a friction coefficient of about 0.1? Like Teflon sliding on Teflon. Anybody know friction coefficient bigger than 1? Yeah, so there's a problem when things stick. The whole concept of friction sort of falls apart like Velcro. And the same with some of these sticky rubbers. But very sticky, soft rubbers that kind of make your hands feel dirty after you just touch them. Sometimes they get up to, I think, almost 2 in the friction coefficient. Okay, how can you measure the friction coefficient? In your car, if you have a low enough gear ratio, for the pulling contest, that's what you should have. You should have cars which are on the border of skidding. Otherwise, it means you could have made your car pull harder by putting on smaller wheels or a different belt ratio or a different gear ratio in your gearbox. If your car is not skidding in the pull competition, it means it could have pulled harder. Right? You want to know how hard can you pull? You could do an experiment and measure the friction coefficient of the rubber in your car, assuming we gave you the mat for the competition, which we haven't given you yet, but as should be his nature, what's the name of the guy who runs the lab? Right, Matt is going to give you Matt, supposedly. So, how do you measure friction coefficient? Well, you measure the force down, and you measure the force sideways that it takes to make it start to slide. Sounds hard to do. Well, there's a simple way to do it. Let's say I want to measure the friction coefficient of nylon on formica. Here's nylon, here's formica. I go like this. Just when it's about to slide, here it is, or sliding slowly, or sliding at steady speed. Right now, the forces are all balanced at this slope. So, if I draw a free body diagram of that situation, nylon on formica, I have a table like this. The table is tipped some angle theta. Here's the little block. I draw a free body diagram. I draw a dotted line. I show this block here. I have a force here of mg, and I have a force here of F. I have a normal force of N, and I'm trying to figure out the ratio of this F to N. So there's some force triangle I can draw like this, or I could work this all out with sum of forces in the x and y direction. but in this case it's easier to draw the force triangle. I have my, I have my mg like this. I have my f like this. I have my n like this. I have a right angle here like this. I know what this slope is. Here's the slope theta. That's the same as this slope over here, theta. So the ratio of f to n is theta. So f over n is equal to, well, it's tangent of theta. So I can say tangent of theta equals mu. And that's why this theta is also the same as what's called the friction angle. So the slope that you just barely slide on, the tangent of that slope is the friction coefficient. It gives you a quick way to measure friction coefficient. Just put something, find the slope it just barely slides on. Any questions about that? Go ahead, ask out loud.
I was asking, what is N?
What is N? N is the force which is perpendicular to the surface when two things are touching. So that goes back over to this picture here. Here's the picture which shows the basic setup with the N and the F. Can you see that?
Something like mg cos theta.
Is it what? What's the magnitude of it? Mg cos theta, but we don't even need to know that for this purpose. We have mg cos theta, mg sin theta. We want to know the ratio of the two is tangent theta. The mg drops out. Yeah?
On the friction graph, is that line an actual line, or do you draw it bitwise like that because it's a roundabout?
I drew it like this so that you could separate it out from the y-axis. So I just meant it to be a line. If you actually did an experiment, you'd collect data like this, like this, like this. You'd probably have some data points up here because there's something called static friction. It's a little harder to get things to start than it is to keep them going. On the other hand, once you get them going slowly, it's a little bit easier. So if you actually did experiments, you'd be getting a collection of points like this. It would depend on the weather and the day and which experiment you did first and which one you did second and so on. Sometimes people like to draw, for those, who's confused about static friction and dynamic friction when they look at this? Who had the thought, where's static friction, where's dynamic friction? Who was thinking that?
Well, isn't it that straight line?
The word static friction has two meanings. One is it's the friction when things are not sliding, which is this line here. So for example, I am standing on this floor. I can promise you this floor has at least a 1/4 degree slope, yet I am not sliding down the floor. So friction is keeping me from sliding. What's the size of that friction force? It's not mu times n. It's less than mu times n. And where am I on this graph? I'm down here, just a little shade above this. You'd have to tip it up to 45 degrees or something close to that for me to slide. That's one version of static friction. Another version is that when you try to slide things, you try, and then you keep trying, and then all of a sudden it breaks loose, and there's a drop here. So sometimes people draw this curve to have a little extension here, and that extension they call the static coefficient of friction. And I would just not trouble your minds with that concept until you really mastered friction without the static coefficient of friction. It's all important, this little difference here. It's not important for understanding gears. It's not important to understand particularly how cars work and when they slide and when you fall on the ice. It's important for some special things. Say you really want to know why doors squeak. You've got to understand that little thing. Say you want to understand how earthquakes work. That's what I did for my PhD. You've got to understand that little thing. Say you want to understand why violins go ah instead of ah. It's that little peak there. But unless you're into these shaking caused by friction, you don't worry about that. Okay, let me just tell you just a couple more uses of the word friction. So people talk about air friction. And what they mean by air friction is not something which is proportional to the squeezing force, but just a force which resists relative motion. So when we have air friction, we have a so-called drag force. And there are two sort of classical drag forces. One is that there's a force proportional to the speed, and the other is proportional to the speed squared. And it's not about squeezing, it's just about resistance to relative motion. And this is what's important for small things. And this is what the guy with the colored chalk was talking about, this linear viscous flow. He's especially interested in it because he's interested in microfluidics. And this is the appropriate drag law for big things. And by big things, I mean ping pong balls and 747s and things like that. And so this is the one that I've been advertising for cars and bicycles because this is a good approximation of the air drag. These are both, this one is actually incredibly accurate. This one is not so accurate. It's not so bad as the sliding friction, but it's, this so-called constant depends on the speed, which means the equation is wrong. But it doesn't depend a huge amount on the speed, only like a factor of 2 or so every now and then.
You see what was the slope? Or no? The C doesn't relate to
The C has to do with, for example, the density of, let's deal with this one, which is the main one. This is the main one for small things, small pipes, teeny pipes, dust falling through the air. This is the one for ping pong balls, baseballs, basketballs, cars, planes, things like that. This constant is proportional to the density of the fluid, it's proportional to the cross-sectional area, and it's proportional to the drag coefficient, which depends on the shape. If things are just kind of random shapes, the number tends to be about 1. If things are super streamlined, it tends to be like 0.1. So it varies by about a factor of 10 depending on the shape. The last use of the word friction is not about a resistance force, but it's about anything which is dissipative. So in your gearboxes, only 75% of the energy that came in goes out, one group measured. Document it well, makes them get a good grade on their final report no matter how bad their car works. What am I talking about? I'll keep my train of thought. You watch, I'll get back to where I was. Now, what was I talking about? Okay, so there's a resistance of the loss of energy in gearboxes, and that's called friction too, because generally friction is dissipative. Dissipative means that somehow mechanical energy turns into heat. If you're ever on this part of the curve, something's getting hot. Something's getting hot. This part of the curve is friction too, the thing which is keeping me sliding on the floor, and nothing's getting hot. So in this sense, friction is not always dissipative. Friction can hold things in place. But there's this other part where you have a dissipative mechanism, like the gearbox. So you talk about friction in the gearbox, meaning some loss in the gearbox. Now, where does that come from? It comes from sliding of solid pieces, but it wouldn't have to. It could be that it came inside the gearbox because it had lots of grease and oil in it to things like this happening inside the gearbox. Or it could even have to do with magnets and eddy currents inside the gearbox causing things to slow down. Any of those things are called friction. Okay. Last thing. Last lecture is going to be Tuesday after Thanksgiving. I do not have a topic planned. I will take requests. So requests can be, I'm confused about X from earlier in the semester. Please talk about it. Or B, I'm curious about Y. You never talked about it all semester. Could you talk about that? So I will pool the requests I get between now and next Monday afternoon, and I will steer my lecture appropriately.